Hey everybody, Dr. A here, and in this video we're going to be providing some background information on what are known as compound systems in a statics environment. So let's go ahead and get started. A compound system is a system that has parts connected by internal hinges. Now you might be thinking, well, wait a second, Dr. A, that sounds a lot like a truss. Well, a truss system, like we talked about in some other videos, is a bit different. A truss system has members connected by smooth internal hinges, yes, but remember, trusses specifically have applied loads or applied forces at joints, okay? Now, a compound system could have loads applied anywhere along the members themselves, okay? So let's get back to our background information, and then we're going to kind of cycle back to this idea of how these systems are loaded later. So we have these systems that have their parts connected by internal hinges. And what are these internal hinges? Well, we probably know what those are at this point in our knowledge. They are smooth pins that transfer horizontal and vertical forces between the connected parts. But what do they not transfer? They do not transfer moments. And the reason is because smooth pins are free to rotate, okay? So we'll close that parentheses off there. Smooth pins are free to rotate, all right? So examples of compound systems include pin-connected beams, frames, and machines. So let's look at an illustration that I already drew out for us. Let's say that we have this compound beam, okay? Now this support here on the left side, I'm calling it support A, that is a fixed support. So you might remember at fixed supports, how many support reactions do we have there? Well, we have 3 of them, right? We're gonna have an AY, we're going to have an AX, and then we have an MA. So 3 support reactions at A. What about on the complete opposite side? We have a roller here at C, and a roller has 1 normal force reaction that is perpendicular to the surface that the roller is resting on. Now, what about what's going on here that's connecting these members together? Well, that is an internal hinge. That's what we call an internal hinge. And we're giving that a label as B. So let me go ahead and label that for us. This right here is an internal hinge, okay? Now, to analyze a compound system, to analyze a system like this, you might be looking at this, you might be saying, well, wait a second, I've got 3 reactions here, I've got a 4th reaction here, so I've got too many unknown reactions for the number of equilibrium equations that I have available to me. Well, so how do we analyze this? We might seem stuck. Well, to analyze compound systems, what we do is we disassemble at the internal hinge, and then we apply equilibrium equations to each individual part, okay? So let's scroll over 1 page, and let's do that together. So let's say we're going to disassemble that figure that we just had, okay? So when we disassemble at the internal hinge, we're going to have that segment AB here, okay? And then we have the little internal hinge there, and we've disassembled at that internal hinge. So I'm going to draw the right part on the right side there, okay? Draw this a little bit straight, okay? So we have this disassembled part. Now, remember, at the left support, we had a fixed support, right? So we had an AY, we have an AX, and we have a moment reaction, MA, all right? MA. And at the opposite side, C, we had a CY. But what's happening at that internal hinge at B? Well, again, those internal hinges can develop 2 forces. So we'll have a horizontal force, BX, and we're going to have a vertical force, BY, that are additional unknowns. Now, this hinge that has these 2 forces, BX and BY, guess what? On the connected part, due to Newton's laws, we will have the same forces, BX and BY, on the other side of that same hinge. But notice they're pointing in the opposite direction of what we drew on the left side. So if we look at that hinge on the left side, I drew BX and BY, BX pointing to the right, BY pointing down. And then on the right side, I drew BX pointing to the left and BY pointing up, okay? Now, you might be looking at this and you might be thinking, well, wait a second, Dr. A, you know, now we have even more unknowns, right? I thought we had 4, now we have even more. Well, we have more unknowns, sure, but we now have 2 parts, okay? So for the sake of completeness, let me go ahead and draw that P here, and we have this uniform load here. It doesn't really matter what the applied loads are at this stage. I just want to emphasize what the reactions and the unknowns are, okay? So what we're going to do to analyze this, what we do is we start analysis with the part having the fewest unknowns, okay? So we have these 2 parts here, okay? We have the segment AB and we have the segment BC. Which one of these 2 parts has fewer unknowns? Well, just look at it. BC has 3 unknowns, right? You have BX, BY, and CY. Those are 3 unknowns. AB has 5 unknowns, MA, AX, AY, and you also have BX and BY, which are also unknowns. So in this particular illustration, we will begin, let me change colors back. We will begin analysis with BC since it has 3 unknowns, okay? And how many equilibrium equations do we have? Well, remember, we have 3 planar rigid body equilibrium equations we can apply to each part. What are the 3 planar, or we sometimes say 2D, rigid body equilibrium equations that we've learned before? Well, we've got some of the forces in the x direction equals 0, some of the forces in the y direction equals 0, and some of the moments about a point equals 0. So, and of course, if we put sign conventions there, we say things pointing to the right are positive, things pointing up are positive, and we typically say things going counterclockwise are positive for moments, okay? Now, the other thing to note here is that unknown reaction directions are assumed initially. Okay, and then what happens? We apply the equilibrium equations. If a reaction comes out negative, it is actually doing what? It is actually pointing opposite of the assumed direction, okay? And so we've seen this concept before, right? We've seen this concept here before when we first learned about calculating unknown forces in systems, okay? So this concludes this video on this background information. And again, I showed just a single illustration of a compound beam system. But remember, these compound systems can exist for frames and machines as well. And we're going to see some examples of those in other videos. So before you forget, don't forget to hit like and subscribe and be on the lookout for other videos and content like this. Thanks for watching.